Thanks, Claes. So as Claes just said, these were some of the collaborators and some of the projects I'm going to talk about today. So from my postdoc in the Max Planck till now. And so I'm going to talk actually about quite old work, but I'll speak to why it's part of my current work as well. So about some of the early work I did in Visual-Vestibular Integration. Then I'll talk about, which is kind of my first MoBI study, which is the vestibular P3. And it follows on from the multisensory one. And then maybe what's more interesting in MoBI is my most recent paper, well, one of the most recent papers on motor preparation in Parkinson's while walking. So I actually chose to go this way because, well, last week you had a whole week about MoBI, a whole couple of days about MoBI, so I thought it'd be nice to talk about something different. I'm going to show that visual and vestibular information is used optimally. I'm actually going to tell you the answer to each of these as we go. I'm going to show you that's true, but you know, it's good to know the answer. I'm going to show that actually self-motion is different from other sensory processes. How we combine body cues and vision is different, and that should impact maybe how we think about MoBI as well. This is all behavioral. And lastly, I'm going to talk about why that might be and how I modeled it. So this is my first neuroscience paper back in 2010 in Journal of Vision. Myself and Jenny Campos, Heinrich Bulthoff was the head of lab there. We followed on from this, doing the similar studies, looking at different aspects of visual-vestibular integration, but I thought it was nice just to start at the beginning. So what is self-motion and what do we need for self-motion? This is just another slide. This is ongoing collaboration with Jenny Campos. We wrote a paper for children. And so this is from that in Frontiers for Young Mind. So for self-motion, and self-motion is particularly of interest because it's actually a truly multisensory event. When we walk, when we move, we use vision, auditory, proprioception, vestibular. You use everything. It's very different from what I would say classically EEG studies consider. Multisensory normally is too, but really self-motion is everything. And also there is the perception of what you're doing and not what the object's doing. So it's really quite different. So that's why I wanted to go through some of the early work on this, just to also frame some of the self-motion work. The vestibular system, our semicircular canals, our rotation, our otoliths are for linear acceleration. And they're so important for eye movements, which most people in EEG hate, but MoBI people love. Head movement, most people in EEG hate, but MoBI people love. And it's the cause of many disorders like vertigo, motion sickness, or falls. And so so what I'm going to call body cues are really inertial cues for the beginning part. So that's my vestibular, and then my visual is my optic flow. There are many, optic flow is, I think, one of the most studied things for behavioral decision making. You know, you have the Shadlin, you have the Newsom papers as well, looking at MT and so forth. And there's a lot of work done on this. But also there's a lot of work more recently, in the last 10, 15 years by Dora Angelaki, looking at visual vestibular integration for self-motion using single cell recordings. But still, self-motion itself is not studied maybe as much. And the question back then, 10 years ago, 11 years ago now, was how do we use the information? How does the brain combine these informations? And so to do this, we used a virtual reality setup, a motion platform on the left there. And we had a star field. The classic thing, the star fields disappear. The only thing that was of note about that was the star field had to be presented in stereo. We had a follow-up study showing that if the star field wasn't presented in stereo, a subset of the people would not fuse the information together. What we believed, and we weren't able to find, but we believe what happened is actually there was a repulsion effect. They believed the body motion was theirs, but they believed the screen moving wasn't theirs, and therefore it became an object motion. And that created a repulsion effect and actually could explain some falls and things, which is so important to understand and address. So I'm going to break it down to the simplest type of paradigm. So what we have here is, and anyone who does EEG can recognize this obviously circle with the little nose is a head. And so what we had was people were moved diagonal to the left or diagonal to the right, and they were asked, and sometimes they were moved physically, sometimes the scene would move, and sometimes they would move together. And so what we do is we'd have different angles, and we get the subject to respond. And from that, we'd get a psychometric function. So we'd have their reliability, how good they were at the task. And this is the multisensory version. So this was the combined thing. So people always know when they're moving at 10 degrees to the left, and -10 is 10 degrees to the left, 10 degrees to the right. But around 2 or 3 degrees, there was some uncertainty. And just on the psychometric function, the PSE is point of subjective quality. And the just noticeable difference is the moment where you notice the difference. Sometimes things are labeled as they should be, sometimes they're not. The JND, which is my measure of reliability, is also indicative of what the slope of the curve is, of the sigmoid. So the steeper the slope, the more accurate people are. The more shallow the slope, the less accurate. And so that's our measure of reliability, how good you are at the task. So we also had this situation, and this is the great thing about doing virtual reality, is you can introduce a conflict. So one kind of conflict we would introduce is the vestibular movement would say they're moving left, and the visual movement would say they're moving right. And then we get the person to respond. And if they responded that they moved left, it means that they relied on their vestibular cue more. And they responded if they moved right, then they used their visual cue more. And so by introducing this conflict, we're able to discern which is weighted more than the others. So introducing it, and this is done. So this was initially done by Mark Ernst and Heinrich and Marty Banks in touch and vision. And they showed that they could use this to understand how it is. So here's the logic of conflict. If something's equally weighted, then what you perceive, if one's to the left, one's to the right, should be in the middle. If it's weighted more to the vestibular, you should say, you should go close to the vestibular response. If it's weighted more visual, you'll go more to the visual response. So it's a very straightforward, observable thing. And so that's what we had. We had a whole sequence like this. So these experiments took like 8 or 9 sessions per person, an hour and a half a session. And for every single person, we get a psychometric function for the visual, a psychometric function for the vestibular. And we be able to say how good they are using their vision alone, their body cues alone, their vestibular, or the two together. And so when we were writing this, this is the beginning of a lot of maximum likelihood stuff. So we were able to say, actually, can we see if the visual information and the body cues are combined in an optimal fashion, which is just a weighted sum. And I've described how you observe it, you do a subtraction, but you can make a prediction as well. And the prediction is the most obvious thing. If you are better using your vision, you should use your vision more. If you're better at using your vestibular, use your vestibular more. So it's a weighted sum of how good you are at the task, which is squared for the sake of it. To get this paper cited so much, we call it Bayesian, but that's just a fancy term. You call it Kalman filter if you're talking to engineers, but really it's adding things together. So the experimental design, there was one vestibular alone condition, which you have to choose left or right. I had 4 visual conditions, 4 multisensory conditions, 5 actually technically, where there was conflicts and the conflicts got larger and left and right. So this was the main result of the study. It was, so on the left here, you see the visual accuracy is around 7 degrees. So that's pretty big, but you know, it's a small movement, it's in the dark. And the visual accuracy was also around that. So the visual accuracy, when the standard was 10 degrees to the left, was around 7 degrees, 6.5. And it has this kind of U-shaped function, but you know, and this had been observed before. What was of note, and is some of the first behavioral human studies to show this is, and it's very nice. The circle is the observed average group data. The black is the predicted using the formula. And what we see is the prediction and the observed data are sitting perfectly on each other. So that was really reassuring. We were really delighted to be able to predict, and that showed that people were using the visual and vestibular information in an optimal fashion. And that similarly, around the same time, Chris Fetch was shown the similar studies in monkeys, but it was lovely to see. But then there was a little issue. So the matching likelihood model that Ernst and people like that had presented early on had shown that I can predict people should get more reliable if they use the 2 cues, but they should be able to predict the weighting as well. And what we found here was the weights weren't predicted in the same way. What we found was actually people biased more towards their body cues. And in some ways, this was frustrating because you want everything to work out perfectly with the model, but maybe it makes more sense. When you're talking about self-motion, maybe it makes more sense to use body cues more. Maybe it makes more sense to weight into your body cue a bit more. So you rely upon the sensory body cue more than you do on the vision. Because also, you know, when you walk, you move your head around. Yes, your vestibular system is moving as well, but your neck muscles, your eyes, you know, there's a lot going on. So they can have a disconnect between your body cues and exactly where you're looking. And to account for that, we extended, I think it was Paul McNeilig's work, and just introduced a prior. And to be as glib as possible, what we did was our data didn't fit, so we just added an extra parameter. And then our data fit kind of, but it did say that actually self-motion is a bit different from other sensory cues. And so that was kind of interesting to us. And so we were happy to have that as a result. And we've reproduced it in a number of studies. And more recently, we've shown actually this even gets more complicated with aging. How older people use vision and vestibular information is a bit more complicated. And there's a lot of breakdown, and they rely upon the wrong signal, which is once again, I think, of interest to anyone doing walking or self-motion studies. So what we showed was participants exhibited a statistically optimal reduction of variance. That means that you get better. If you have 1 + 1 is 2. Well, 1 + 1 weighted is equal to square root 2, actually, is really the formula. But the other thing is, it didn't perfectly predict which way you would rely upon more. It would predict about how you could get better at the task, but you would bias towards one cue or the other. And for that reason, we had to introduce a prior, and therefore that's why we used the word Bayesian in the title, because prior information impacted the perception. And that prior information is so important for older groups and, well, many different groups, because a bad prior will completely negate a good combination. Following on that, other people, once again, Dora Angelakis' group and Puget and Drogowitz have done similar heading studies. But in this one is a bit only slightly different. In my one, you had to wait to respond. So you got 2 options and you responded. They did it such that people would click as fast as they could. And so they had this data, which is very similar to mine. And more recently with my new PhD student, we're actually developing mathematical models to see if we can reproduce this sensory integration model by modeling neurons. And this is very new stuff, but we're at least able to produce some of the, and I'm just going to make you assume that as I flick back and forth, you can see, oh, they look kind of similar. And so we're moving forward to think about how we can make models to look at sensory integration for self-motion. So this led on to, and kind of logically led on to, okay, well, we've seen behaviorally the vestibular signal being used, but electrophysiologically speaking, Klaus can vouch for this, like back in 2000, so I think I started this study 2008, 2009. There was very few people doing movement in EEG, and I was ignorant of EEG back then, so I didn't see why you couldn't. So I wanted to do a vestibular P3 experiment, a vestibular oddball experiment. So I wanted to see, could we get a neurophysiological measure into decision-making during self-motion, which I used in my P3 response. Can a body cue without vision elicit a P3 response? The reason why I was asking that is because the vestibular signal, it has no specific loci. It's processed everywhere, and therefore maybe it isn't processed similar to other sensory cues. So that's, well, like it was a question. Is it comparable to other responses? That would once again confirm, is it comparable to other sensory cues? Is it used in the same way? And it was feasible to do it. Is it feasible to do single student participant subjects? So the experiment was very simple. Actually, the first one we did, which mirrored by coincidence, but it made sense, the study that I did with Philip and everyone in Einstein, John, and then very similar to the one Klaus had out at that time, where we did a visual target detection task, where there was a standard target, a standard and a target. And we did this study just see is, in this study, we moved the person back and forth, and we want to see, could we get P3 while someone was moving on the platform, and we got it. So we knew we could get clean data. Once again, I have to say, naivety and ignorance was the best thing that we could have, because if I'd been someone who'd done EEG before this, I would have immediately said doing self-motion was impossible. And we saw a nice P3 in this, and the topo looked very nice. So to do a vestibular oddball task, and I think now I design it slightly differently, but you know, you design it with what you have. We had a vestibular oddball task where there's a diagonal left target or a diagonal right target. Classic P3 task where 80% standard, 20% target, 15 participants, and that's myself, a much younger version of myself, sitting on the platform for the recording. So it was just as simple as we moved the person. Standard was, this was counterbalanced, standard was left, left, left. And as soon as they got the target, they clicked the button. And so we chose an angle of 45. It probably was much bigger than we should have, but once again, we'd never seen anything like this. We couldn't find any other papers like it, so we wanted to make sure that it was detectable and there wasn't an issue with detectability. So it's our neural marker for change detection. And, well, of course, this is no surprise, since we're talking about it, we found one. Now, there's a couple of things that's different from the classic P3. The first is that P3 or the P300 is normally considered to happen at 300 milliseconds. That's the real problem sometimes with naming something with a number in it. Luckily, we read around and we saw that people had done something like an olfactory P3, and that P3 was delayed. And also coinciding with this time, two of my collaborators, Simon Kelly and Redmond O'Connell, were actually looking at slow decision making and showed that actually the P3 could be very long, and it normally just peaks along with decision. And when you do a long movement, you can't make the decision early on, it has to progress. So we had a look at topography. So the significant electrodes were at the back of the head, where the P3 was, very typical of the P3. So that was really reassuring. And that's the topo map. I should say, the student I did this with, Hugh, he went to loads of trouble and he made quite a popular ICA analysis toolbox to analyze this data. And now it does look messy, but that's, if anyone does EEG, they know human subjects are messy, and even getting a P3. We did individual bootstrapping analysis, and we found actually everyone had something that was significant around the time period it should be significant. You know, they are messy looking, but that was once again reassuring. As I said, Hugh Nolan, co-first author in this, built a full toolbox to do ICA on the data, but it turns out we didn't have to. Actually, the data were relatively clean. We just had to be careful with the filtering, and that was it. So in my mind, and I can be contradicted, I think it was the first time anyone had shown a vestibular heading P3, which is nice. It once again shows that body cues are treated like other cues, how it's processed and how decisions are made. It was a window into decision making in self-motion. And also it was nice that we were able to do some bootstrapping to look at the individual subjects. I would say that we didn't move on much from this. Hugh finished his PhD and I moved on from Max Planck. We did some other analysis showing that actually if you lock it to responses, it's even sharper, but overall we were pretty happy with this study coming out at the time. So now This is a massive leap in time, and maybe it feels a massive leap in type, but my time in the Albert Einstein, as I said, I helped set up their VR lab, which was a treadmill with a lot of tinfoil for electrical things. We did a lot of walking EEG experiments. And so if you read the work by Brenda Malcolm or Pierre Filippo, that's all the study. So, but this is my most recent walking experiment, which is with the group in Ireland in people with Parkinson's. And walking experiments is particularly interesting in people with Parkinson's. We want to investigate the impact of walking on a simple behavioral task in people with Parkinson's. And the manipulation here is between people with Parkinson's with freezing a gait and without freezing a gait. Freezing a gait is a progression in severity of disease that impacts our walking. And we have young controls as well. We use mobile brain imaging to investigate how the walking impacts their motor and how it impacts their decision, their CPP, P3. CPP is what Simon and Redmond call the central parietal positivity. But also we were interested to see, and this is in line with earlier work with John Fox and Pierre Filippo de Sanctis and Brenda Malcolm, looking at some early automatic responses, the N2. So a bit about Parkinson's. Parkinson's neurodegenerative disorder, loss of dopamine. Dopaminergic signals, you have tremor, and the symptom that was most prominent and most of interest in this was freezing a gait. There are many non-motor conditions which are very debilitating, and dopamine is the treatment. So a bit about freezing a gait. Intermittent gait disturbance, you get glued to the ground, very disturbing, more prominent with late stage Parkinson's. It can be induced by a visual signal, but it can be hard to induce. My co-author on this, Conor Fearon, who is a neurologist and an engineer, spent his PhD looking at freezing a gait. 60% of Parkinson's, and it affects falls, causes falls. Now, once again, Parkinson's is the one is very interesting and so important to analyze, but also it can inform us a bit about natural aging process as well as the normal walking. Freezing a gait is very poorly understood. There's very little effective treatment and difficult study, and it varies across people. So it's a complicated disorder. So our experiment, very simple. I think I did the reverse of a lot of people. Is I went from the Max Planck where you have gold to using a Wii and a stepping pad. But the thing is, the results were the same. If you design a nice experiment and you try to control as best you can, you don't need gold, but gold is nice. So it's a very simple experiment. The corridor was there, but wasn't part of the study. It was just part of something else. And they just had to click a button when they saw an X. So this is a classic P3 task. They did it when stepping and sitting. So, but we had three groups. We had a freezing group, we had a non-freezing group. So FAG plus means you're freezing, FAG minus means you're not freezing, and we have young controls as well. The group sizes were small, and that is a shame, but that's life. We had two conditions: sitting, sit, and stepping in place. Just use the BioSemi kit, and the filter was 0.1 to 30. And the other thing I did was, instead of doing the ICA, which was an intentional decision, we just used CSD, and that was to separate the sources. So the behavioral effect is pretty nice. What we have here is, so this is just a sitting task. Each dot is an individual. The black dots are the group average. On the left, you see the FOG, the freezing group, non-freezing group, and then the controls on the right. So the range of participants is actually quite consistent for sitting. No surprise, the younger controls are a bit faster, but when sitting, everyone's kind of consistent at the task. So there's no reaction time difference between the Parkinson groups. There is a difference between the control. But for the stepping condition, and this is lovely to see the behavior, and that's why I think behavior is so important. Because if you have a behavioral effect, you definitely will see an electrophysiological effect. If you don't have a behavioral effect, you might see an electrical EEG effect. And I'm going to illustrate that with this data as well. What we see here is for the group on the far left, which is the freezing group, as soon as they have to step in place, every single person got slower. Every single person, their reaction time, their response time was slower. While in the non-freezing group, still Parkinson's, they actually got faster when stepping in place. And with the younger group, they all got faster. Now, it's not substantial, but it is significant. In the young group, it's to get the ire of statisticians, it's marginally significant in the non-freezing group. But we'd seen actually similar behavioral thing in our work with Philip, that actually some people got a bit better and quicker at the tasks they're doing when they're walking. Now, the stepping wasn't, it was their own stepping pace. If we'd forced them to go faster, I completely would believe this effect would completely go on. But if they're in an environment they feel safe in, you probably get this benefit. And that behavioral benefit is going to be important for the interpretation of the EEG data. So the EEG results. So we have our standard, our target, and then our P3, the standard minus target. And note this is once again CSD, and the P3 for the young people is coinciding with the dashed line, which is the reaction time. So that looks quite nice. But that's sitting, and it'd be bad if I didn't have a nice looking P3 for that. For the FOG plus group for sitting, we have a nice looking P3. Once again, these are people with Parkinson's, there's tremors. So even to get that was nice. For the FOG minus, that's people with Parkinson's without freezing a gait, very similar looking response. And lastly, the control group I just showed you. So that's very consistent between the three groups, which is nice. And I'll talk about analyzing that, but in theory, that's a null result because there's no manipulation of group here. All groups are consistent for the P3. So we see it now. What was nice and why we used the CSD was because of Simon and Redden's work. They were looking at separating motor. You could, of course, do this in a dipole coordinate system as well in a similar fashion. But what we note here is there was this frontal activity in the freezing group when sitting. It's kind of small bit there for the non-freezing group, the middle group, but it's not, you know, it's not so wrong, and it definitely isn't there for the young group. So in line with what other people have looked at, we looked at the lateralized readiness potential, looking at the electrodes to left and right and taking their subtraction to look at the motor activity. And what we found was just in the sitting condition alone, and now this is so important, the behavior was the same in the sitting condition between the freezing and non-freezing group. But the EEG now shows that there was larger motor activity for the freezing group. So it seems, and the non-freezing group and the controls had very similar motor activity, which suggests that actually the freezing group with more Parkinson, they can do the task fine, but they really need to recruit their motor cortex, which makes sense. It's a motor-related disorder, and therefore maybe they need to recruit more motor. But the less progressed people with Parkinson's didn't have that. So then we get to stepping. So our MoBI moment, we had pretty nice looking P3s across, and the three groups: freezing, non-freezing, and controls. And so the P3s, you see here that the reaction time is much delayed. The P3 is not peaking in the same clean way. When we response locked it, it looked a bit cleaner, but it wasn't a big thing. But they're relatively similar, not identical, but relatively similar. But once again, this is people with Parkinson's who have a movement disorder stepping in place. So even to have something that's even usable was a delight. So our first call was, once again, let's look at the motor activity, because that's where we show the difference. And so what I would say from this is, while not identical, it's quite a similar decision-making process between the groups. Once again, it's the motor. So when people with Parkinson's are stepping and doing the pressing task, they need to recruit their motor cortex for longer, and maintain it for longer. And this can, of course, result in fatigue. The recruitment of resources is a tactic, and it's a wonderful tactic to do it, but it then can impact things like reaction times. So why don't we look across? So if we look within groups, now I'm just looking at the P3 or the CPP, what we see is the FOG group in the middle and the control group on the right, their sitting and stepping conditions look identical within themselves. Not so for the freezing group. We have an early difference. We have this N2 difference. This automatic response isn't there for the freezing group. And so that means that this allocation of resources to recruit for the motor means that maybe some early automatic responses that benefit them when doing reaction time in the N2 has been associated with this kind of thing is gone. And that would then knock on. It's not a cognitive issue. It's a motor thing that feeds into the cognitive. So behaviour letter showed that people with Parkinson with freezing and gait had a slower response times while stepping compared to sitting. But it was the opposite for the freezing and gait. People with Parkinson without freezing and gait and the controls, they actually got better. And that's always nice to see sometimes. It was a surprise, but it's nice to see. The difference seen in the motor was very significant. I don't want to use that term, but it was significant for both the sitting and walking, but only for the freezing group. And then we have this combination between the N2. The P3 is consistent between conditions within group, but it's the N2 that really pops out to be quite different in that freezing group. So hopefully you'll see that like coming in from the behavioral side was so important, specifically in the last one, because that behavioral result would have been nice to see. And, you know, that's an interesting behavioral. People with Parkinson's are slower when walking, if they think, but it was the EEG that really dug into it. And that's the strength of something like mobile brain imaging, but I'm preaching to the choir here. And then when we go back in time to my early visual-vestibular stuff, it has made me think a lot about self-motion in maybe different ways, and how important it is that we pull in different information all the time from different areas, and how it's a truly multisensory event. So, and hopefully more and more understanding of self-motion and self-motion disorders. So thanks everyone for listening. And once again, my long-standing collaborators. I'm sure there are many other people I forgot to thank here as well. So thank you.